Wonderful. Well, why don't we get going next so we can have a great discussion? Thank you, everyone, for joining us here on Friday, March 21st. I'm Sandlin Buxner. I am the Director of Team Development for the SHIELD Drive Science Center, and with me is Nick, who is the deputy, and we are so thrilled to be hosting. Marav is actually not here today for a really, really fun reason. We're so excited that one of her students, Eric Powell, is defending his PhD today, and we're so thrilled because Eric is the first end-to-end PhD of SHIELD, which means he began his studies and will be finalizing all of his papers as part of the Drive Center. And so we're really excited to highlight this new generation of scientists. And so more on that, but we just want to let you know that's where a good chunk of folks are. And so we just want to again welcome you. We are so thrilled. We are number 3 of our Voyager StoryCorps as part of the webinar series. We will continue again having these really wonderful discussions as a way to engage everyone and kind of what has happened and what is to come as we think about really exploring the solar system.
And we're coming up on the 50th anniversary of Voyager.
And so again, today we have John Belcher and Ralph McNutt who are going to talk with each other and with us. And so we invite you to ask questions. This is your time really to ask all those things you wanted to know as they chat with each other. And we will again continue our conversations. And so we're going to be doing 50 years of plasma measurements. And we do have some wonderful experts with us. Hey, Nick.
Oh, yeah. Oh, this is me. Okay, great. Hi, I'm Nick Gross, also with SHIELD. We give you a quick introduction to SHIELD. Part of what SHIELD is trying to study is the sun's heliosphere. As Marav likes to say, that we're not just moving through space, but we've got this bubble around us coming from the sun, and you can see that bubble in examples of other astrospheres around other stars. And so we're trying to understand both our own astrosphere, our own heliosphere, and the boundary between the solar wind and the interstellar medium, and to understand our own, but also to understand what's happening with other stars. We have, based on the computer simulations that are being developed by the entire SHIELD collaboration, um, and we have one possible structure of this heliosphere that has it goes out to about 100 AU, 100 astronomical units, and has this interesting structure. One of the goals of SHIELD is to try and understand. Nope. Next slide. One of the goals of SHIELD is to try and understand the physics that's going on at the edge of our solar system, at that boundary between the solar wind and the interstellar medium, and to create a digital twin. Not everybody agrees, and part of the work that Marav did to build SHIELD was to bring together a lot of experts, both with diverse backgrounds and diverse thoughts about what the structure of the heliosphere is, and both observationalists and computer modelers and theorists, to try and come together and come to some consensus, or explore what that structure is. And so we've got a number of different questions, but also a number of different data sources, including the ongoing Voyager missions, which our distinguished guests, Ralph McNutt and John Belcher, will be talking about some of their experiences with the Voyager missions, but also New Horizons, Cassini, IBEX, and then different modeling techniques that are going on. As a center, we not only are trying to build these collaborations, but also then build the community and build the group that's going to be exploring the outer heliosphere. So bringing in new researchers, young like undergraduates working, getting exposed to heliophysics for the first time, and then graduate students becoming experts in their area, and then doing some bench strength development with some of the early career folks to bring them in and to become leaders in the field.
And then,
So,
yeah, we just want to
mhm,
let you know we'll have a webinar more for professional learning events. So we'll be announcing that very soon. And then we will continue in May for our next Voyager StoryCorps. And then, of course, you can find us on the web and on social media and all these places. And so with that,
right,
we want to get going.
great. So I guess we'll maybe turn it over to Ralph and John. This is a very informal uh, uh, conversation. And I don't know do we want to start with a couple of pictures?
Yeah, that sounds good to me. Yep.
Is
In
this where you want
particular,
to?
the picture on the left is her bridge, the father of all this.
Whoop.
And in the middle are John and Ralph. And in the far right is Stan Obert. I put his picture in because he actually developed the program to analyze the full response to the instrument, along with Alan Barnett, which was really crucial to doing a huge amount of science on the Voyager probe. So I wanted to include Stan in there as well.
And sorry, which one is Stan?
Stan is the fellow on the right for the far right picture.
Great. So, and then you've got some pictures of the original instrument.
Right. The plot in the middle is just the plot summarizing the entire mission out to, oh, geez, 120 AU. There's the termination shock. Incidentally, let me mention a little bit of my history with space physics. My thesis advisor at Caltech was Leverett Davis. His first graduate student, no, his first graduate student, that's right, was Eugene Parker. Of course, Parker predicted the solar wind, and Davis actually coined the term heliosphere. He was the first person to predict the distance to the interstellar medium, to the termination shock. And in part, that was because he had a history of being an expert in the interstellar magnetic field, so he knew a lot about the interstellar environment and knew enough to guess about pressures, etc., so that he could estimate the distance to the heliopause. And then the cup on the right is our side-looking cup, which had a number of names, people put in there. If you look at the very top, we have a "Live Free or Die," which is the state of New Hampshire's motto. Our chief engineer, Bob Butler, his first name there is Robert Bertla, was from New Hampshire, and that's why we have "Live Free or Die" on that. This is a poor man's golden record, just the people who were involved in building the spacecraft. The instrument, I'm sorry.
So how did that work in terms of signing? What is that? What is that plate there that they're signing?
It's a collector on the back of the Faraday cups have a collector at the rear end of everything. There's a grid that you can see in the front. So this is actually the collector used to collect the currents. Um, and I don't know how they collected the signatures. I certainly don't remember ever being asked for my signature. So I don't know whether they made all this up or what, but it was a surprise to me when I saw it.
How does the picture on the right and the picture on the left, are they related?
Yeah, the picture on the far left, that is the side-looking sensor, and then on the far right, it's just a close-up of the side-looking sensor.
So this is the picture. Right here is the picture on the right.
Right.
Yeah.
And this instrument, this is flight spare, is in the MIT Museum. If you want to see the flight spare, it is on exhibit at the MIT Museum.
Great. Should I go on to the next set of pictures?
Ralph, are you still there?
Oh, I'm still here. I'm just being quiet because I have to be careful because John was my thesis advisor. So and he's doing a great job too.
Right.
I don't think he can revoke your thesis proactive or retroactively.
Well,
No, they're not.
I don't know, but I've gotten paranoid in my old age. So what are the John and I were kind of emailing back and forth about the side sensor, and I think I remember Herb telling me that when Butler put the live free or die on the top of the collector plates, that he didn't bother telling anybody about that. And NASA found out about that after the launch, and Herb, I think I remember Herb saying he had a lot of explaining to do
Yeah.
because that was not an authorized thing to put on two probes going to interstellar space eventually.
Right.
Um, so we could go on to either pictures, but I'd like to know a little bit more about how you each got involved or drawn into the Voyager team and uh were introduced to working on this project.
My answer is short, it was John's fault.
Right.
John, your turn.
Uh, I was a graduate student, and Leverett Davis had a collaboration with Ed Smith at JPL. Ed Smith is a magnetometer guy and had a magnetometer on board Mariner 5, and Herb had the plasma probe on board Mariner 5. So after launch and after we got a lot of data, we all went to Iowa, I think, and sat down and looked at all the data. So that's how I came to know Herb and Al in particular. So when I finished my thesis working on that data, Herb offered me a postdoc back at MIT, which I accepted. So so I came back and I guess it was early 70s, and when I first came back, we started writing the proposal for Voyager, and it was accepted. I had something to do with it, but not a lot. And then, of course, we got Voyager, and then that became sort of my principal occupation for the next many years. And uh, Ralph was applied as a graduate student. What was your motivation for applying to MIT, Ralph? I don't ever remember talking to you about that.
Oh, well, so I grew up in Fort Worth, Texas, and I went to Texas A&M as an undergraduate. And I wanted to see what the rest of the country looked like, and I wanted to go to the East Coast. So when I was applying for graduate school, I applied to who did I apply to? I applied to MIT, I applied to Columbia, I applied to Cornell, and I applied to Princeton. Princeton turned me down. I got accepted at MIT and I guess at MIT and Columbia and Cornell, and so I had never been east of the Mississippi River before. So I managed to make a trip. I made the arrangements to make a trip up, and I guess John, for whatever reason, ended up being either volunteered or was volunteered um, to meet this kid who apparently was potentially interested in MIT. I remember, John, you took me to some hamburger joint up at Harvard Square. I don't even remember what the name of the thing was, but had a good conversation with you. And I remember from there, I ended up going to Columbia and then going to Cornell. Cornell was just frozen over. This was must have been in January or February. And I remember getting back and trying to figure out where I wanted to go, and MIT was the one that had all the different things in physics going on, and I'd always been interested in space stuff anyway for a long, long time. And so I ended up selecting to come to MIT as a graduate student, and I kind of vaguely remember that at some point, and there was a research assistantship, and so I mean this is John, if there was a problem with me being there, well, it was all your fault. Um, but I just remember being introduced to Herb and talking to him, and he said, "Well, we've got this instrument that's going on the Voyagers that we're going to be launching, and would you be interested in being in working on some of that?" And I was like, "Where do I sign before you change your mind?"
Right, right.
So that's the longish version.
Yeah, and I should say that Ralph was instrumental in getting the nonlinear analysis code in sort of production shape, even though Alan Barnett and Stan Olbert put it together. When it really came to be applied to data, as far as I know, it was basically Ralph putting all that together.
Well, it was definitely a team effort, and yeah, I had a little bit to do with it.
Yeah, and for example, when we went past the EO flux tube, we got a very good set of measurements, but the flow was very oblique. So you really needed to know the full response function of the planet to be able to get quantitative answers about the deflection of the flow around the EO flux tube. And that was Alan Barnett's
Yep.
thesis.
Yeah, and John, I vaguely remember you looking at the whole Alfvén wing thing and double checking that from the speed and the deflection, you could work out the Alfvén speed, and I think that the numbers that were coming out of Alan's code were like, I think it was like within 5% of the density that you were getting from the other analysis.
Right.
And which was, I think at the time, I think Al Lazarus had touted that as the best density measurement that had ever been made with one of these things.
Oh, yeah. Uh-huh.
And I vaguely remember talking with it was either with Herb or with Al one time, and of course they'd been involved with engineering these things for a long time. And two of the other people that had been associated with the group were Vatanis Vasiliunas and George Sisko, who had both been at MIT before me. And I don't know, John, how you overlapped with George and Vatanis, but I remember Al saying something about one of the funniest things that he'd ever heard was that the two of them had been arguing with each other about something or other, and they came to see Al and Herb, who were in the lab, and Al said, "Well, I think he said it was George that said to him, well, we were having this argument about how accurately you can get the density from a Faraday cup and whether it was 5% or 15%." And Al said, Herb and I started hysterically laughing. And and he said, we just kept laughing for about 15 minutes, and the two of them were looking at us very quizzically. And finally we kind of composed ourselves, and Herb was like, if we get the density to within an order of magnitude, we're doing really good with these things. So it's all a learning process, and of course that was back in the very very beginnings of all of a lot of this stuff, and everyone was still learning their way. John, I don't know if you remember that story or not.
No, that one I don't remember. I do have a little anecdote about the EO flux tube, which is interesting in the sense that we missed going straight through the EO flux tube. We went ahead of the wing, the Alfvén wing, and the reason we went ahead of it was because do the trajectory calculation, they just used the vacuum magnetic field of Jupiter, which I think they had a pretty good idea about. But what that did not take into account was the fact that there was all this plasma there. So the Alfvén speed is really low. If the Alfvén speed had been much, much higher, then the vacuum prediction would be the right way to model it. But in fact, the Alfvén speed was much slower. The Alfvén wing is swept back, and we didn't take that into account. So it swept back, and we went to a place where we thought it would be, but it swept back from that place. But actually, in retrospect, I think it was good that we didn't go straight through it. We were far enough away that we could use some distance approximations, and it made it much easier to figure out what was going on with our data, I think.
So we have some experts that are on, but we also have some people who might not be aware of what you mean by the IO flux tube. Um, could you explain a little bit about that? And did you know that it was already existed, that it was there?
Oh yeah,
For the flyby?
the EO flux tube is a well-known puzzle. There's a guy named Big. You look at radio bursts from Jupiter, and they're EO bursts, so that when if the line from the Earth to Jupiter to EO is a 90-degree angle, you get a lot of burst, a lot of radio burst. And Big first found out that correlation, and the explanation is that there's beams of electrons coming down from EO that hit the foot of the flux tube, and they put out emission in a very flat cone that's almost 90 degrees to the flux tube. So that's why you see it preferentially when EO is 90 degrees from the Earth Jupiter line. But there had been a lot of speculation about what was going on, a lot of models of the EO flux tube, and it was one of the high points of the science. We wanted to see what indeed that interaction was.
Great. So these are magnetic field lines that are connecting Jupiter to Io, and then that's where
Right, right. Because of EO's motion through the co-rotating plasma, there's about 1,000,000-volt potential difference across EO. That's a motional EMF, V cross B, but nonetheless, it's 1,000,000 volts. And in EO's rest frame, that's enough to drive 1,000,000 amps that flow along the flux tube down to Jupiter's ionosphere and back. So 1,000,000 times 1,000,000 is 10 to the 12 watts. That's sort of the energy that's being put out by the EO interactions, which is quite a terawatt. That's a pretty good amount of energy. Yeah.
Great. Should we look at a few more pictures?
Sure.
So who are these guys?
So in the middle, I think I was the one that sent these to you. So in the middle, that's on the left is Bruno Rossi, and then the other one is Herb Bridge. And again, as John said, Herb is the original PI on Voyager, and they had Rossi and Bridge had actually put together an instrument for trying to look at the interplanetary plasma, and the publication of that's on the right side. That's from October of 1960. This is when it was still developed. And the first of these Faraday cups flew on Explorer 10 in 1961. And they didn't actually get to see the solar wind because they were still inside of part of the magnetopause of the Earth, or maybe just within the bow shock. Um, because there had been all of this debate because of Gene Parker that John had talked about earlier, who had come up with this theory about there being a solar wind. And so once that the space age had started, there was this race on to try to find it. Konstantin Gringaus in Russia, the Soviet Union at the time, had an instrument. I think he was on Sputnik 2, and Herb and Rossi had this experiment again on Explorer 10. And then finally, the solar wind was actually verified with the instrument that Snyder and Neugebauer had on board Mariner 2 that went to Venus in 1962. And were able to show that, yes, there really was a solar wind, and indeed Gene had been right. And the two pictures over on the left, far left-hand side, the top one is Bruno, and the bottom one is Herb during World War II, because the place that Herb and Bruno met were at Los Alamos on the Manhattan Project, building the atomic bomb. And Bruno was a good friend of Fermi's. He was ran one of the groups, and Herb was Bruno's assistant, and that's how they got to know each other uh, back during World War II. And I don't know how many people out there have actually seen the movie Oppenheimer, but if you did, right before the Trinity test shot was done in 1945 at Alamogordo, it shows there being this incredible thunderstorm that was going on. And I remember at one point Herb telling me, and the bomb itself was on the top of a 150-foot tall tower above the desert floor, and there was lightning all over the place. And there's about 1,000 pounds of high explosive in the device. And Herb told me that he was one of the people that got to climb to the top of that tower during the lightning storm to check all of the connections to the high explosives for the test that was going to be going off at about 7 hours later at 5 in the morning. And of course, it worked. And as you say, the rest is history. And Herb and Bruno both ended up at MIT, and Bruno had gone there. He had to leave Italy in, I think, in 37 because Bruno's wife was Jewish, and they had to get out, as did the Fermis from Italy, and ended up coming to the U.S. And then Bruno ended up at MIT and started up X-ray astronomy and started up space plasma physics. John, I don't know what else you'd like to add to that. But that's
Well,
what I
other than
remember.
yeah, that just that Herb was a graduate student in chemistry at Cornell when the war really got going and he got drafted. They were looking for anybody that had any remote sense of physics, and he got
Yep.
drafted to go. They sent him off to Los Alamos, which is where he met Bruno.
Yeah, and I vaguely remember Herb saying that his first assignment was to take a letter from some appropriate official within the U.S. government to go talk to the head of the physics department at Harvard to let him know that the U.S. government was requisitioning the Harvard cyclotron, and Herb was there to take it apart, and it would be returned at the end of the war. And Herb supervised them disassembling the Harvard cyclotron, putting it on a train in Boston. It was shipped by train to Lamy, New Mexico, offloaded there, and then taken up to the top of the plateau at Los Alamos, where they set it up as part of the beginning of setting up some of the scientific equipment to work on the Manhattan Project for the atomic bomb.
Have cyclotron will travel.
Exactly. I mean, Herb and Bruno were both incredible experimental physicists.
So I assume these are pictures of the launch?
That's Voyager 1. They're a little blurry. I took those. I was actually I lucked out. I actually got Herb invited me to come out to help support the launch and then the instrument turn on Voyager 1. And so I can't even remember. I was out there with Jim Sullivan, who was also on the group, and we were someplace where you could see the launch site. This was with my parents' Argus C3 slide camera using Kodachrome film, and that was the Voyager 1 launch. And I remember after we lost sight of it, going to mission control to watch the um, spacecraft come around to the correct side of the Earth to do the trans-Jupiter injection with the upper stage. Herb said something about, yeah, I was sitting in this room when Mariner 3 failed, and I thought, oh God, what a great thing to be thinking about. But Voyager 1, as had Voyager 2 that launched earlier, both got off, got injected to Jupiter, and we were on our way. And I think
And
John had talked about these that with the again that's Herb and me and John and Al Lazarus across the bottom. There's a picture of John on the left with some of the other people in our one of the briefing rooms at out at JPL that for where all the scientists gathered. Of course, Ed Stone was a project scientist, was running those, and then I talked Herb into standing in front of, and that was, I guess that was at the Neptune encounter, and then the one on the right is Herb at the Neptune encounter, and that was the big status board that had been up for a long time for Voyagers, and I said, Herb, why don't you come over here and let me take a picture of you? So I managed to snap a picture of him when we were out there for the Neptune flyby in '89.
you get this info on Twitter now at Voyager, the Voyager spacecraft post a tweet every day about where they are.
Yeah, things had changed a little bit since 1989.
Yeah, let me just say a little bit about the encounters. The encounters were incredibly competitive between the various teams. The big competition was to get into the press conferences. And if you think that science is looking for truth and beauty, you're wrong. It's all about ego. So one of the things that we did that I remember very distinctly was that Neptune is pretty empty, but the magnetic field is offset by a good amount, 50 or 60 degrees. And that was a big thing, was whether there's going to be an offset or not. And we managed to get that first because the plasma in a co-rotating magnetosphere with an offset sits at the magnetic equator, or it sits somewhere between the magnetic equator and the centrifugal equator, which quite frankly, I can't remember what is. But nonetheless, if you look at where the plasma is sitting, that tells you where the magnetic equator is and therefore tells you what the tilt is. So there was a fellow postdoc with us whose name I forget, who was sitting up in the middle of the night, saw where the plasma was pooling and figured out the tilt, which got us into the press conference, which was a big deal to get into the press conference, especially when you're beating out the magnetometer team led by Norman Ness, who I had a lot of interesting interactions with when I was a graduate student. So it was fun to get the result before the magnetometer team got it.
You may remember we also got press conference at the Uranus flyby.
Mm-hmm.
I stood up, and Ralph was supposed to do it, but because of the Challenger disaster, it was delayed by a couple of days.
Yep.
So he had to go back and teach at MIT. So I was volunteered to do the press conference for PLS. And I trained the night before, talking to various people at JPL, and I came in and I said, oh, the magnetosphere of Jupiter is this weird and wonderful thing. We're tipped on its side. And everybody got excited, and I got a lot of emails about that. And then I remember John Belcher saying to me, how can you stand up and say that public? We were horrified.
Hi, Fran. It's good to hear from you.
I finally got in to join you.
Excellent.
Yeah, there was actually a whole crew of people who went to. Fran, did you go to all the encounters? I can't remember.
I went to the Jupiter ones. I was at Goddard and Saturn,
Right.
and then which was very interesting too. That was a different crew. We hung out with the magnetometer people, though they were very secretive about the EO data. You remember in the flyby?
Oh yes, they were.
Yeah.
Yeah.
But the Uranus and Neptune, I was at JPL, which was very exciting.
So you went to all the encounters.
Yep.
Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep. Yep.
Wouldn't miss them.
Oh no, I used to have dreams about having an encounter. It was such an incredibly intense experience because you would plan for these things for 2 years. There was a huge amount of argument that went on as to what you were going to do with limited resources on the spacecraft. And by the time it got there, you knew every hour of what was happening in the 24 hours where you were really getting interesting data. So it was quite an intense experience.
What I remember from Voyager 1 at Jupiter is that I had been doing a graduate student comprehensive exam on predicting what we would see with a PLS instrument based on the ground-based observations of emission from sulfur and oxygen lines. So people may remember that the volcanism of Io was detected partly by looking at the ground-based observations, telescopes, and then we finally flew through it. And what you're seeing in the middle here is John Belcher in the middle, Ralph on the right, John Richardson on the left. They're looking at these printouts, and these are where you would have a printout with a pen that would scratch across and then scratch again across and so on. And this would show the wiggly lines of the spectra, the data coming out of the PLS plasma instrument. And I had predicted that when we went from the hot region in the middle magnetosphere to the colder region in the torus, the wiggles in the plasma instrument would stick up like fingers. And I will never forget seeing those fingers start to appear on the scratching across on the plot.
Actually, that's a wonderful story. I had never heard that.
Oh, really? Okay.
Yeah.
That was your qualifying exam.
Yeah.
Yeah.
So then I went on and wrote my PhD on the data. So, yeah. Ralph and I split the magnetosphere into, I did the inner part and he did the outer part.
Right. And everybody's right. These were you kind of got on adrenaline and it just kept going.
Actually, let me give you one remembrance. We were sitting down at Goddard, and there was a lot of remote observations of the hydrogen and sulfur, and then they were quoting densities, and they were quoting incredible densities. Nobody expected to see these densities. That's why we underestimated the Alfvén speed, because nobody
Right.
knew that. So we're sitting there. I remember Al Lazarus and I at lunch. I don't remember anybody else there, but we were sitting there thinking, well, what gain state should we put the instrument in? Because we had a lot of choices and a big range, probably 4 orders of magnitude in sensitivity. And we looked at the numbers when we did a calculation, and we said we should put it in the least sensitive gain. And I remember both of us looking at each other saying, are we really going to do that? But we finally convinced ourselves that that was the right thing to do. And indeed, we did saturate in 1 or 2
Yeah.
modes, but it was indeed the right thing to do to make it as insensitive as possible. Just a huge amount of plasma there.
Yeah, I think there was just one saturated spectrum. I probably got it in the files that are behind me here in my office.
Yeah, that was an M mode. There, the L
Yeah.
mode saturated a lot.
Oh, yeah, that's right. Yeah, the L mode saturated a lot. Yeah.
But there was only one M mode that saturated.
But it was interesting because the UV guys on approach were saying, it's bright, it's bright, it's bright. And they were right. There was a lot of stuff there.
So I've stopped sharing my screen, but we can always go back to that if we decide that there's more pictures involved. And given that Fran is adding to the conversation, I'm going to pin her up onto the big board here. So I'll invite people. I have a couple of questions that I want to ask, but I'll also invite people to either put questions in chat or raise your hand, or and I think everybody can unmute themselves and ask a question. So feel free to do that. I have a couple of questions. Let's start with this. So recently, the plasma instrument got turned off
Right.
for, well, we lost what so this is this is the first question. What did it feel like when you lost the Voyager 1 instrument? When and do we know what happened to it, and how did that feel, right? But
Well, I was really mad because that meant that the first cross of the termination shock was we weren't on. We had failed on Voyager 1. So that
Right.
was, yeah. But actually, Ralph was really involved in trying to get it to come back on, much more so than I was. So maybe Ralph could give you some of the blow-by-blow description of thermal cycling the instrument.
Well, yeah, it was it was a noble cause, but the windmill won. Um, it was funny because, and John, you'll remember this, that Voyager 1, there was a period of time after launch that it lost most of its sensitivity, I think in 1978.
Right.
And I don't think anybody ever quite figured out what the problem was, is from what I remember. I do know that that they had been trying to thermally cycle the instrument to see if that maybe that would do something that would get it back on again. And I know that I remember Herb telling me that he'd been out at JPL with Ernie Fransgroth, who was our lead for the instrument out there, and they were getting ready to change the heater settings, I think, and all of a sudden the thing came on, and Herb, they were getting ready to radiate the command, and Herb told Ernie, and Ernie went running. According to Herb, Ernie went running off to the ACE, which was where that the commands were broadcast from, basically waving his arms, saying, "Don't send the command to Voyager to turn off the heater on the PLS instrument." And at that point, the instrument was fine, and that's why we got all of the great EO Taurus data that
Right.
Fran was
Right.
able to work
Right.
her magic on. And we had gotten up to, I think it was at the Voyager 1 encounter with Saturn, and I wasn't there. I was off doing some other stuff for a couple of years, but I came back. And but I guess what had happened was that the spacecraft had been turned in sort of a different direction that allowed the UVS instrument to be able to see Saturn. And they turned the spacecraft back, and they had to do it with the jets. There are no reaction wheels on board. And so you basically fired the jets, started the spacecraft spinning, then fired the jets again to stop the spin. And when they fired the jets to stop the spin, the plasma instrument also failed, and it was just like gone. And at one point, as John was saying, had gotten involved later on with when they were talking about basically turning off the cameras and descoping, all of the remote sensing instruments, and having the heliospheric mission about, well, why don't we try one last time to see if we could try to thermally cycle it? If a couple of wires had pulled loose, which is sort of what the thought had been, maybe that you could change the thermal characteristics and get them close enough to form what's called a vacuum weld, and at least be able to try to trigger it, because we thought that the Joe Benzak, who was the program manager and had been at APL or APL, God, MIT for a long time, had thought that it was in the control circuitry, and maybe it was a small wire that had let go. And so I got involved with trying to turn heaters off and trying to cool it down, and then trying to heat it back up again. But nothing ever worked. So we never got the instrument back after that. And but going back over the engineering data from the Voyager 1 at Saturn when it failed, I think we got the engineering readouts about once every minute, and to within a minute, when they hit the jets to stop the spacecraft from rotating at outbound from Saturn, that's when all the temperatures changed, and that's when then the instrument failed. And so there was something that was just on the hairy edge of being loose, and apparently the firing the jets was just enough to shake it loose, and that was the end of that. Oh well. Space is a tricky business, and it's hard to do this stuff, and you need a little bit of luck along with an incredible amount of skill to pull this stuff off. But we've had those combinations on Voyager and still do.
Yeah, well, even more emotional was when we turned off the Voyager 2 instrument, because that was premeditated. We knew that was going to happen. And, well, they told us it was going to happen. We didn't really get much choice in it. But they're having real power problems, and we were told we were going to be turned off in a couple of months or 6 months, and then all of a sudden it's 2 weeks, and all of a sudden it's next week we're going to turn you off. So that's hard to watch an experiment that has been sitting there faithfully for 47 years, returning data, to watch it be turned off like that. Yeah.
Yeah, I think actually I was looking at some other stuff, and I think that Voyager 1 and Voyager 2 have set the record for the longest run of particles and plasma and magnetic field data of any spacecraft that anybody has ever launched.
As far as I know, that's true, right?
And it looks like there's a question in the chat from Marcia Neugebauer. Hi, Marcia. What are Voyager 1 and Voyager 2 doing now? John, you want to take that one?
Well, Voyager 2 has still got the magnetometer working, and I believe the 2 energetic particle experiments are working. And Voyager 1 and the plasma wave experiment. So if you ask what science they're doing, I think they're looking at shocks in the interstellar medium, which are caused by the expansion of the heliosphere. It's a shock in the interstellar medium, but it's a shock that's created because of the pushing out of the heliosphere. Those are and of course, the energetic particle people are doing what they always do, which I never did really understand.
And the Marcia that asked that question, and again, it's good to hear from her. She is the Marcia Neugebauer that worked on Mariner 2 that found the solar wind back in 1962.
Right.
I'm glad you remember.
Well, of course I remember. It's good to hear from you.
The other thing I'm curious about is, I don't know how much of a surprise that the Voyager mission has lasted this long, and what did you learn about operating a mission for this period of time, and how does that, and here's I'm going to feed you one, Ralph. How does that influence Interstellar or other future missions that let's just say future missions that might be planned.
There you go. That's politically correct. Well, 50 years is a good aim point. I mean, it's basically set by the de facto half-life of a radioisotope power supply. These things run on plutonium-238. That's what's been running Voyager for all these years. It's what's running New Horizons right now. The isotope's got a half-life of about a little over 80 years, but the half-life of the power supply is more like around 45 to 47 to 50, because you've got degradations in the materials that convert the heat into electricity. And so we're down to about, on the Voyagers, we're down to about half the initial power that were coming out at the launch. And of course, the original design lifetime for Voyager 1 and Voyager 2 is 4.5 years. So, and I found that in an AIAA paper. So when we passed 45 years, we'd outlasted the original warranty by a factor of 10. And so right now we lose about 4 watts about 4 watts of power a year. And so what's happening is the spacecraft's cooling off, and the real trick is that we use hydrazine on board the Voyagers in order to fire the jets to keep the high gain antenna pointed back at the Earth. And we're not that far above the freezing point of hydrazine. So we're playing tag with having enough heat to have heaters on to run some of the instruments and not freezing the fuel lines, and so be able to lose contact from the Earth with the Earth that way. So 50 years is a good aim point, but it's kind of right there at what one can technically do. And I remember asking Chris Jones, who was out at JPL, about, well, how do what do you do with something like Voyager to enable it to last so long? And he said, have a really good parts program when you're putting the thing together. And of course, there's a lot of luck involved too.
Yeah.
John, you want to add to that one?
Yeah, one of the things I would just remark on, it really is not planning for the future because you can't plan for this, but the thing returned data for 47 years. Do you know how many generations of computer technology 40 years is? We have analyzed data from this spacecraft with everything from an IBM 7090 to your latest CentOS Linux distribution. It's just been an incredible mishmash of code written over many, many years and many, many graduate students. So it was a real challenge to actually put something together that you could archive that would have all the data and all the software in some way that was runnable. So, but we've done that.
Fran, what's your
So
card of numbers?
these are punch cards.
Ah,
And we did our first Voyager 1 at Jupiter, Voyager 2 at Jupiter with punch cards. I'm pretty sure we used punch cards back then. And
yes.
we had to program in Fortran. And so it's Fortran 66 because this is early. And we used mag tapes and then printout with the scratchy pen going across the paper and the paper going around. So it was slow.
So Fran has reminded me that my thesis analysis card deck was 1,500 IBM punch cards that I had typed out myself on the puncher, because that's what we did. And one night over at the Laboratory for Nuclear Science computer that was an IBM 360, I dropped the box. Because we were able to take over the computer at about 2 in the morning because we needed so much of the darn computer. And luckily I somehow managed to get the cards put back together, but I was ready to go jump in the Charles River.
Had you done that trick where you take a pen and you draw it diagonally across the top of the cards so that then you can stack them back together?
Oh, why would you want to waste your time doing that, Fran?
I did that because my first job was filling in these punch cards. My first job as a graduate student at MIT, doing that.
I'm not sure if if the question is ironic or not, but there's a question in chat.
Well, there, Fran is showing you a punch card.
I mean, it's literally a line of code, right? But it's a line of code that's been not digitized, but quite yet. But it's
Well, it's an IBM punch card, and there are it's either what is it? It's either 6 or 7 spaces at the front where the line number goes, and then you've got another 72 punch columns to put in whatever the code is, it gets coded up. And those were actually invented to originally do the collation of the 1890 census of the United States.
Oh, didn't realize that.
I didn't realize that.
Yep.
Interesting. Yeah.
And the reason that those things are the size that they are is they're the same size as an 1890 US $10 bill. And one of the problems they were having was figuring out how in the world to be able to keep up with these damn things. And the Treasury Department had been throwing all these boxes away that they had originally been stacking the $10 bills in coming off of the printing presses. And that's why an IBM card is the size of an IBM card. It was the size of a $10 bill in 1890. I think you can find that on the it's on some website out there. I can't remember which one it is.
There's a question from Derek. Derek, you can feel free to unmute yourself. This may also be a cue for John Richardson to jump in, if or Ralph and John Belcher. I think you can unmute yourself, Derek, if you want to ask it out loud. Maybe not.
Hi guys, can you hear me?
Yes.
Oh, perfect. Thank you. Yeah, just looking ahead, if possible. I know that NASA just introduced at least a plan to look at approximately 20 exoplanets. So I was wondering if you guys can maybe connect the dots between what Voyager has already done and what it can do in the future in relation to that question. Maybe for the future scientists up and coming, some of the data that they're going to encounter in the future and how Voyager would have helped with that.
I'll jump in and just and as a lead in for John. John was talking about Leverett Davis and looking at trying to figure out the size of the heliosphere. And I think that paper was published in PhysRev in 1955 that had Davis's prediction of about 100 astronomical units. And one of the things, I was going back through some papers. There's a paper, John, that you published that I was a co-author on. Several of us were co-authors on trying to predict where the termination shock of the solar wind was going to be. And I think it was back in like 1992. And the joke at the time was always that the termination shock was located 5 years later than wherever Voyager was at the time that the question got asked, because that was really the big question. So, we know what kind of a star that the sun is, and we've now got a better idea of how big that the sun's astrosphere, the heliosphere, is. John Richardson. Oh, come on, guys. Fran, say something. You're in love with exoplanets, right?
So I'm gonna channel Marav. And so I'm not an expert on this, but I'll do my best to channel Marav, and part of the goal of SHIELD is to understand these interactions between the stellar winds and the interstellar medium, and how that's going to influence habitability of both the Earth but then potentially other planets if we have the physics worked out from this. So the fact that Voyager is out there telling us what the conditions are, the boundary conditions for the simulations, if you will. And also about, this whole thing about the bow wave in front of the heliosphere is kind of neat, that it's kind of surfing that bow wave, and you're seeing these pulses coming off of the heliosphere is very neat to me. But so that, I think that's one of the ways that we can try and understand habitability is by understanding what's happening to the other astrospheres and the radiation environment and the space environment around exoplanets. All right.
And say something. Fran,
Well,
Awesome. Thank you.
John,
great.
I'm hogging too much of the conversation. You need to jump in.
Well, of course, as you well know, we were never designed to measure the conditions in the interstellar medium. You really need another mission to go out there properly instrumented to to measure the interstellar plasma. Yes.
Gee, somebody should get on that.
Yeah, right.
Where's the Interstellar website? What are I'll pull it up and that'll be our sort of last image. What is there a website for Interstellar?
There's a website from the study that APL did. It's at interstellarprobe one word.jhuapl.edu. At least I think it's still there.
There's a Wikipedia page for it. Yeah, there is.
I
So
think it's interesting. What's interesting is that the estimates were so different. You know, the early estimates, the heliosphere was so small, and it just, you know, it ended up being huge. I mean, I think that's pretty interesting that we were chasing it and chasing it and chasing it. It just took
Well,
such a long
I
time.
think the interesting thing is that Leverett was pretty darn close.
Yeah.
Yeah.
Yeah,
I
it is
know
interesting. Yeah.
I know there was one early estimate that got it down to like about 1.5 AU, and then Pioneer 10 and 11 took care of that.
Yeah.
so
Well, it's really amazing that we got there. I remember at one point, Don Gurnett, for reasons that I don't remember, was saying that it was at 400 AU. He estimates, and we would never have gotten to 400 AU.
Right.
I remember just thinking, "Will you shut up already?"
Yes, because there wouldn't have been a press conference then, John.
which is any good storytelling sort of brings us back to the beginning. So so I'll let I don't know if there are any last words about your recollections or your feelings for this mission. And if there are any last questions, people are starting to sign off. We're past the top of the hour.
All right.
But if there are any last questions, feel free to put them in chat or just unmute yourself and jump in.
Yeah,
But
let me jump in with one final comment that we hadn't brought up, but I think is actually important, and that is, you know, Voyager would not have worked if it had not been for Ed Stone as project scientist. You know, and I mean, I don't know about Fran and John, but I was certainly spoiled because I thought that Ed Stone was what project scientists were always like. Not necessarily the case. But seriously though, I mean, Ed was just an absolutely incredible person in every direction I could think of, and if it weren't for Ed, we wouldn't still be operating now. I'm totally convinced of that.
It's very interesting that he at the flybys and in between, I'm sure too, but I remember the flybys, every day he'd be talking to the different instrument teams and learning very quickly what they were seeing and what they were doing. All of them, everything from remote sensing to spectroscopy to, you know, the geology and as well as the space physics. And he understood it all very quickly, brought it all together, as well as understanding the mission management and the mission and the spacecraft. He really was amazing. And I thought all mission scientists would be like that, but he was really stood out as exceptional.
Yeah, he did. I remember coming back to MIT saying, Why doesn't our president act like Ed Stone? He got me spoiled.
I think it spoiled all of us, John.
Yeah.
Okay, well, with that, I'd like to thank both our scheduled speakers, and thank you, Fran. So also for jumping in and sharing your recollections of this wonderful mission and these measurements. And we will watch out for our advertising for our next webinar, and which will be in May. Although we are also trying to schedule something for April. And so, and we'll continue these Voyager StoryCorps recollections to share with everybody, and pass on that understanding to the next generation. All right.
Great.
Thank you all.
Thank you
Thanks.
for the invite.
Yeah, thank you.